So in this video we are going to introduce Hamilton mechanics and derive the Hamilton equations. So the big difference between the Hamilton formalism and the Lagrangian formalism is that we pass from a formalism that uses a scalar function of coordinates, velocities and time, as the Lagrangian is, to a formalism that uses a function, still a scalar function, of position, momenta and time. So in order to get this Hamiltonian, because this new function is called Hamiltonian, we are going to start from the Lagrangian and do something that mathematically is called Legendre Transformation. So it's a fancy name, but it's a quite easy concept. I can write the differential of the Lagrangian as the sum over the degrees of freedom of the derivation of the Lagrangian according to the position with the differential of the position plus the sum over the degrees of freedom of the partial derivative of the Lagrangian according to velocities, differential of the velocities. We are assuming that there is no explicit time dependence, because if we work in an inertial reference system, the partial time derivative of the Lagrangian is 0. At this point, we already know what this and this are. In fact, this is the time derivative of the momentum and this is the momentum. Thus, we can write this as the sum over E of the time derivative of momentum with the differential of position plus the sum over E of the sum over E of the momentum with the derivative with the differential of the velocities. Now, this part, with a small mathematical trick, could be written as the differential of PE QI dot minus the sum of QI dot times the differential of the momentum. So actually, if you make this differential, we'll get the sum of these two. So this one can be written as this difference. It's a little trick, nothing more. Thus, the differential of the Lagrangian has the form of the sum over the time derivative of the momenta, the differential of position, plus this strange differential we just inserted, minus the sum of the velocities times the differential of the momentum. Now, arrived at this point, I'm going to write it up here. So, starting to write from the top again, this thing can be remixed where I will bring this, maybe if I write what it was, it's the differential of the Lagrangian. I'm moving this on the other side of the equation. You can get that the differential of the Lagrangian minus the sum over pi qi dot is equal to what remains. So the time derivative of the momenta multiplied the differential of the position minus the sum of the time derivative of the velocities of the position with the differential of the momenta. This is a minus. Now, you may notice that this is already something that we might be interested in, because it depends on positions and on the momenta. But there is still one step, because this is only quite similar to something we already know, but isn't exactly what we want it to be. So if we change signs everywhere, so by simply changing the signs, so by simply changing the signs, now we start recognizing it. This is the total energy of the system. That is also called the Lagrangian of the system. So the Lagrangian is nothing more than the total energy of the system. So actually the kinetic energy plus the potential energy, where the Lagrangian was minus. This is plus, nothing more. So by rewriting it, we can say that the differential of the Lagrangian is pi dot dqi plus qi dot dpi. So at this point we can derive what we are really interested in. So this is quite interesting, already quite interesting, because it's a differential of the Hamiltonian, and as said, it depends on positions and coordinates. But now we need an equation that we can use to get the equations of motion. So it's quite easy. We can simply construct them starting by this differential. In fact, we might say that pi dot should be equal to minus the partial derivative of the Hamiltonian depending on the positions. Because as you see, here are the positions. The same thing for the velocities. That shall be the partial derivative of the Hamiltonian depending on the momenta. Because as you see, here is the derivative of the differential of the momenta and the differential of the Hamiltonian. So these are Hamilton's equations, also known as canonical equations, because they're so important they have even been given this other alternative name. With this one, we can derive every kind of equations of motion of the system. The most interesting difference between Hamilton's equations and Lagrange's equation is that with the Lagrange you had S, where S is the number of the degrees of freedom of the system. Second order differential equations. Here we have a system of 2 times S first order differential equations. So double as much equations, but they are all first order and not second order anymore. Now, 2 interesting properties of the Hamiltonian. One is that the total time derivative of the Hamiltonian is equal to the partial time derivative of the Hamiltonian. Thus, if the Hamiltonian has no explicit time dependence, so we are in an inertial reference system, in a closed inertial reference system, the Hamiltonian won't change in time. Another interesting thing is that if we have some kind of parameter, lambda, from which the Lagrangian and the Hamiltonian can depend and can change, any kind of parameter, it's very interesting because the partial derivative depending on this parameter lambda with constant position and momenta will be equal to minus the partial derivative of the Lagrangian according to the exact same parameter with constant positions and velocities. So if we know the partial time derivative of one of the 2 functions, we already know the partial time derivative of the other one. This can be very interesting to apply it to the time derivative. Because if we are in a situation where we, for example, know that the Lagrangian has no explicit time dependence, neither the Hamiltonian has. And actually, we know that if they have wrong, And actually, as we know, if the Hamiltonian doesn't have an explicit time dependence, it will actually be time independent completely. Its time derivative will be 0. The Hamiltonian also introduces the concept of phase space. You may have heard about it or will hear about it 1000 times talking about statistical thermodynamics, for example, but in general talking about the energy surface of a system. So, what is this phase space? It's simple. It's nothing more than actually the space in which we work when we are using the Hamiltonian approach. So, it's a space that can be represented like a Cartesian one, where we have the position and the momenta. Of course, if we have s degrees of freedom, it will be 2s dimensional. So in this case, if it's simply like this, it would be a one-dimensional system. And each particle of the system will have a certain value of coordinate and of momentum. So it will be one point somewhere in this space. So actually you can do quite a lot of things, and we will see them more later on, by considering the phase space instead of considering the physical space, because actually we're quite more interested in knowing in the same moment the position, the momenta of the system, instead of only knowing the positions. It's quite similar to what we did in the Lagrangian, and in this case it's quite often used as actually a space, to be considered as a space, and it has even a name, as said, phase space.